All right, welcome everybody to this session. This is track 2, the Maple in Mathematics session on Tuesday. We will get started with the first presentation in the session, which is by Ryan Sandford. Ryan, take it away.
Hi, thank you everyone for coming. And today we're going to be talking about computing intersection multiplicities with the use of regular chains. And this is based on work with Jürgen Gerhard and Mark Marino Mazza. So to start, what is an intersection multiplicity? An intersection multiplicity generalizes the notion of the multiplicity of a root of a polynomial, but for more than one polynomial. And it's useful because it helps us understand the behavior of an algebraic set at a point. So if that point was singular and you could not approximate it by, let's say, a tangent space, then tools like the tangent cone and intersection multiplicity help us understand the singularity, or in a sense, tell us how complex it is. So here we have an elliptical curve and a line. There's both a transverse and a tangential intersection, and this would have an intersection multiplicity of 3 in this case. So one thing you might want to know is, how do we compute these intersection multiplicities? And the first way to do that would be to compute a standard basis. And that's implemented and described in singular. But at times one may wish to avoid the use of standard bases. So that's when you want to start thinking about standard basis free intersection multiplicity algorithms. And what those often do is they look at this other algorithm, Fulton's bivariate intersection multiplicity algorithm. And that essentially takes 2 polynomials in 2 variables and applies a set of rewrite rules to elegantly simplify the system to something we can compute. So I'm going to show, these are his rewrite rules, or his 7 properties. Very quickly, the first few just kind of set the stage and say it'll be a not negative integer, or kind of the base case here in red. And we can apply a change of coordinates or reorder our polynomials. And then at the bottom here, we have a splitting property and another one that says we can add copies of the polynomials to each other. So you can start to see how maybe this could be used to build an algorithm or some kind of procedure. And we talk about both of these more in the presentation, but really quickly, here is his bivariate algorithm that the other algorithms would use. So he assumes a general variable ordering that has nothing to do with the geometry of the input. It's arbitrary. You consider the point to be the origin because you can always assume this. You can apply one of the properties. We check the base case, and then we give a criteria for when we're able to split. Once we split, we get these smaller intersection multiplicity computations, which eventually would give you termination. And then this blue case essentially just says we can always get to that splitting case, so we can always reduce there. And that's kind of the feel of the algorithm that we're going to be talking about. So in Maple, there's a command called intersection multiplicity. And what this does is it applies a reduction criteria based on tangent cones to reduce to that algorithm I just showed you, Fulton's algorithm. Now, unfortunately, this criterion does not always hold, though. And that's kind of what we're talking about today, because in Cask, a new standard basis free algorithm was investigated, where what we did was we extended Fulton's bivariate algorithm to the n-variate setting. So today, what we want to talk about is what we did to the intersection multiplicity command. So we adapted this command to include both of these standard basis free algorithms. So it would apply first this new generalization that was given in Cask, and then the standard basis free algorithm, which uses tangent cones already in Maple, and sees if one of them succeeds, because they're both partial algorithms. And then moreover, we implemented this algorithm, and then we extended the theory to handle non-rational coordinates. And then we benchmarked it to see, okay, well, is this new approach faster? Do we get anything from it? And that's what we're going to talk about really quickly. So as you saw, Fulton's algorithm kind of assumed the point was the origin, and the generalization does the same thing. Now, if the point had rational coordinates, then it's very easy to adapt Fulton's algorithm, or you could just apply an affine change of coordinates. It's not too bad. but sometimes you'll want to work with non-rational coordinates. You'll have to work with algebraic numbers, and these kind of cause their own challenges and issues. So one natural solution to this would be to encode your point as a solution to a system of polynomial equations. And we can do that using a regular chain. And a regular chain is essentially a triangular system of equations that have algorithmic properties, as Mark talked about yesterday, and they encode a finite set of points. So now we adapt the theory of this algorithm to handle a system of polynomial equations rather than a tuple of numbers. And in doing that, because these zero-dimensional regular chains encode multiple points, those points could have multiple intersection multiplicities. So now instead of returning a number, in our new extension of this algorithm, we have to return the intersection multiplicity as well as the points they correspond to, given by another zero-dimensional regular chain. So that was the first thing we did. We implemented it and we extended the theory, and then we tried to benchmark it. And here you can see our legend. Basically, method 1 and time 1 will refer to this new Fulton generalization, and method 2 and time 2 refer to the time and what was computed by what already existed in Maple. So this is some of our own examples. The first 8 tests basically just use this system down here and scale it up for larger and larger n. And what we see is that the generalization of Fulton's algorithm experience a significant performance improvement as the size of the system scales, even for a simple system. So by the time n equals 25, we're getting about a 14-minute time difference, which is pretty significant. And then if you make the system a little more complex, as we see in this last test here, where we only have 6 variables, you get essentially the discrepancy between the 2 algorithms becomes more pronounced. We also have some other examples here where the generalization of Fulton's algorithm succeeds, but the other one doesn't. But these are all tests that we've made. So here we look at some tests in the literature, and we'll see that sometimes they both fail, but often this new approach will succeed in cases the other one failed. And if they both succeed, we still get a speed up of about 1 or 2 seconds, even though it's a small input system. So we can see a speed up and we can see it's computing more cases. But depending on what variable ordering we choose, sometimes this new one will fail too. So we have, this motivates the idea of doing a hybrid approach, because now we have examples where the other algorithm will succeed, where this new generalization fails. So that's why we're thinking we should take a hybrid algorithm to compute intersection multiplicities here. So that's basically what we did. We implemented this new algorithm. We combined it with the old one. We extended it to handle non-rational coordinates, and then we benchmarked the results. How much time do I have left?
You have about 3 minutes left. So I think it might be a good idea to switch to questions now, if that's okay.
Yeah, I agree. Are there any questions?
All right. So I have one question here that I got sent. So you talk in the extended presentation about a situation with a bad ordering. What I didn't quite understand is, does the ordering affect the answer? So if that's not the case, could you potentially recognize a bad variable ordering and then compute the answer with a different variable ordering? Or would that be asking a different question, essentially?
No, so I think what you're saying is, if we change the variable ordering, does it affect the intersection multiplicity itself, like the actual number? And the answer to that is no. But it can affect what we return, whether we return fail, as in we weren't able to apply this procedure successfully, or if we return the actual intersection multiplicity. And that's what this example is saying here. But the variable ordering has nothing to do with the actual geometry of what we're trying to study. It's just an arbitrary ordering that is needed for the procedure.
Understood. So then I guess the second half of the question is, can you recognize, so would there be possibly in the future, I don't know, a method to distinguish if you get a failure case, distinguish a case where where it is not going to be possible to get the answer in any way, or whether you might be able to get the right answer by looking at a different variable ordering?
Yeah, that's a very interesting question, because it's kind of hard to say before runtime how these rewrite rules will be applied. Because as we rewrite the system, it changes quite a bit, and it's hard to say what's going to happen down the line. But that kind of motivates a very interesting research question is, well, is there something we can look for there? And right now, what I kind of look for is if you have a lower variable in the ordering, which has a coefficient, which is like a higher variable in the ordering, or like a non-invertible coefficient, that's usually what's going to cause it to fail if that coefficient doesn't get eliminated. So you might be able to design like a heuristic to check for that.
Understood. Great. We have 30 seconds for one last short question from Michael Monaghan, who asks, what do you mean by a standard basis in this context?
What do I mean by a standard basis? So I believe that's the ideal in the local ring, like the leading term ideal considered in the local ring at P, if I'm saying that correctly. Does that kind of answer it? I'm basing it off of this book on Singular, and they have a theorem that talks about basically how you can rewrite the definition of intersection multiplicity to an equivalent definition using a standard basis.
Okay, thank you. Thanks, Ryan. If you could stop sharing your screen, then I'd like to introduce the next speaker, which is Juan Pablo Gonzalez Trochez. Juan is going to talk. Is going to give the next presentation, and could you start, Juan? Go ahead.
Hello, I will start sharing my screen now. Share. Okay. Oops. Good morning. My name is Juan Pablo Gonzalez Trochez, and I'm going to present a Maple implementation of a modular algorithm for computing the common zeros of a polynomial and a regular change. This is a joint work with Matt Calder, Professor Mark Moreno-Massa, and Eric Postman. The agenda for today, I'm first going to explain the non-modular approach. Then I will explain a modular approach for solving our problem, then experimentations, and finally some conclusions. So first, let K be a field with characteristic 0 or sufficiently large characteristic. Let F, T, and B be non-constant polynomials in the variables x greater than y greater than z. And let's assume that the set formed by little t and b is a regular change. We will call that capital T. And the main variable of t is going to be x, and the main variable of b is going to be y. Also, let's assume that the main variable of f is x. Our goal is to compute the intersection between the derived variety of f and the quasi-component of the regular change t. That is, we want to compute E regular change such that the intersection between the derived variety of f and the quasi-component of capital T is contained in the union of the quasi-components of this regular change. So we are going to now explain our genericity assumptions. We will call little r and L the subresultants of index 0 and index 1 respectively between T and F when the main degree of T is greater or equal than the main degree of F. Our first assumption is going to be that R is going to be non-constant with main variable Y. Now let S and G be the subresultant of index 0 and index 1 between R and B, and denote that S bar the square part of the square free part of S. Sorry. Our second hypothesis is going to be that the set S bar G and L will form a regular change. Thanks to this, we will have some consequence. The first one is that S bar G and L are going to be non-constant with respect to the variables Z, Y, and X. That the initial of G is going to be invertible mode S bar, and the initial of L is going to be invertible mode the ideal generated by S bar and G. Our third hypothesis is going to be that T is invertible modulo the ideal generated by S bar and G. And as a consequence of this, we will have that the intersection between the algebraic variety of F and the algebraic variety of S bar, G, and T is going to be equal to the algebraic variety of S bar, G, and L. And if we put all this together, we will have that the algebraic variety of F, T, and B is equal to the algebraic variety of S bar, G, and L. And this will, under our hypothesis, we'll have that the intersection between our input polynomials is going to be equal to the algebraic variety that is generated by our output polynomials S bar, G, and L. So now the modular method. What is important about the modular method that we are implementing is that the subresultants R, L, S, and G will be computed by evaluation and interpolation. We use the Vesu bound of the input polynomials, the variety of the input polynomials, to this evaluation and interpolation process. And we are going to verify our genericity assumptions as we recover S, L, S, and G. And if we find that they are not met, we will just send an error. And the last one is that we are using basic well-optimized functions of Maple. In particular, we use the MOPI1 library. Our experimentations. First, consider the prime characteristic that we have here. If we input the polynomials T, B, and F of degree 9, this one that we have here, we will see that the intersect time of the current algorithm is near 300 seconds. The modular method that we are proposing is just 30 seconds. And we see that this is a really good first, a really promising example of what we can do with this modular method. About the experimentations, in lower degree, we see that always the intercept command is better than the intercept by specialization command, that is our modular method. But as the degrees of T, B, and F get higher and higher, we start to see examples where the intercept command behave worse than the modular method. And we see a really good promising example of this. And we can see this is the example that I just showed before. And we see that the times here in some cases are much better than the intercept command. So the conclusions, we present in this work an algorithm for solving a trivariate system of polynomials, F, T, and B equals 0. And we, for the call of the intercept command of Maple, and we are going to, we're trying to extend this to the n variable cases, and we also are trying to relax our genericity assumptions to make our algorithm more general. Furthermore, about the practical aspects, we see that the experimentation that we did in Maple brings promising results for our modular method. Also, there is large room for improvement. we can use something that is called speculative algorithm for computing subresultants. And these are asymptotically fast algorithms that compute the subresultant of index 0 and 1 without computing the other subresultants. And if we need the other subresultants, then we are able to resume our computations and get them. So we can further improve the current version of our algorithm. Thank you very much. That's all that I have to say.
Thank you, Juan. I have one question from Michael Monaghan, who asks how many variables are being interpolated?
We do all the whole process by interpolation. We only compute subresultants of polynomials in one variable, and then we use we created an algorithm to computing subresultant chains in polynomials in two variables inspired by an algorithm from Mike Monaghan. And then in the main algorithm, we do interpolation of the third variable. So we're doing interpolation of the variables, the two variables, yeah. Basically. But at the end of the day, we're only we're seeing our polynomials as
okay.
So okay. Does that answer your question?
I think we'll leave it. Oh, Mike says yes. Excellent. So we have time for one more short question. How was the evaluation and interpolation done to compute the subresultants? And did you use sparse interpolation? I guess the question is somewhat related to Mike's question.
Okay, so we first evaluate in the last variable that is set. Now we have two polynomials in two variables. So now we can use our implementation for subresultants in polynomials in two variables. This implementation is done in a modular function too, and relies in our fast implementation of the subresultant chains for polynomials in one variable that is done using MOP1 completely. So then after that, we get the coefficients of our polynomials, but we're seeing our polynomials as polynomials in the variables x and y. So what we are interpolating here is always polynomials in the variable z, and for this we rely basically in the interpolate command of the MOP1 library.
Okay, I think we'll cut it off there. And with that, thank you, Juan. If you could stop your screen sharing, then we'll move on to the next presenter, who is Laureano Gonzalez-Vega, who will be talking about using Maple to study Bohemian correlation matrices. The floor is yours, Laureano.
Thank you very much, Eric. I will start sharing my screen. So I think that you are already seeing my screen. So first of all, I would like to thank Rob Correlation by introducing myself in or about Bohemian matrices, and to Nick Hygan for proposing me the problem at hand I am going to describe today. I am considering Bohemian matrices. A Bohemian matrix family is a set of matrices where the free entries come from a finite population. And those Bohemian matrices I am going to consider today are those where the population is, for example, 0, 1, or -1, 0, and 1, or even -1 and 1. So the Bohemian matrix in this case I am going to consider are a square matrix, and I will denote by Bn n01, for example, the set of Bohemian matrices, dimension n, where the entries are 0 and 1, and similarly in the other cases. The problem at hand, and introduce myself by Nick Hagan, was just to determine the number of correlation matrices in the set, for example, of Bohemian matrices of dimension n, square matrices with entries in the set 0 and 1. Do not forget that a correlation matrix is a square symmetric matrix where we have only ones into the diagonal and where all the eigenvalues are non-negative. So 3 years ago in the Manchester Bohemian workshop, Nick Huygens presented this table where he has computed the number of correlation matrices, the third column, in the set of Bohemian square matrices with entries in 0, 1. So next line into this table was just computed in 1 day during the Manchester workshop, and we got this number, almost more than 4,000 matrices are Bohemian and correlation matrices when we consider dimension 8. So having these numbers, 5, 15, 52, and so on, we moved to the online Nick Sloan Encyclopedia of Integral Sequence, and we discovered that these sequences correspond to the Bell numbers. So this was for us a very good news because it provides a conjecture where to prove that, of course, the number of Bohemian correlation matrices of dimension n with entries 0 and 1 are just Bell numbers. Well, we are not so lucky because we also discovered that already Robert Israel has just discovered it, and this information comes from the online encyclopedia, where he describes exactly the formula we were looking for. But this open a way of performing more experiments dealing with these Bohemian matrices with different populations and just to know how many of them are correlations. The most important thing for us in this case was the way of computing this number, because the first approach, Nick Huygens, was using MATLAB for computing eigenvalues and to decide when all of them were non-negative. And even initially, for n equal to 7, there was some initially wrong results due to precision problems in MATLAB. We were lucky enough in the sense that we were able to characterize a correlation matrix by just using only the sign of the coefficients of the characteristic polynomial. All eigenvalues of A are non-negative if and only if we have alternating signs for the coefficients of the characteristic polynomial, and so we avoid completely computing root of polynomials. We avoid completely rounding errors when deciding if these real roots are positive or not. And so in this way, Maple was and is extremely useful just to decide and to compute first characteristic polynomials of matrices with inter entries and also to decide the sign. No? In this line, this characterization, moreover, introduce a closed form characterization of correlation matrix in terms of polynomial inequalities. Here you have the result for n equal to 3, but also you can imagine that characterization is with more polynomials, more inequalities for dimensions bigger than 3. So just showing you how Maple was used to analyze and to study the set of Bohemian matrices when we have fixed the population, what's happening with those matrices which are correlation matrices. We have a set of 5 results I will introduce later now, but the idea, the approach was always first to use Maple to make a conjecture, and then we have been successful when proving this conjecture. For example, if fixing the population -1, 0, and 1, we have that all matrices which are correlations, except the identity, are singular. Continuing with the same population, we have that the eigenvalues of these Bohemian correlation matrices with this population, all of these eigenvalues belong to the set between integer numbers between 0 and n. And in all cases, we have at least one multiple eigenvalue. Moving to the population -1 and 1, we have that all Bohemian correlation matrices with this population have exactly the same characteristic polynomial, and we have been able to derive in this case the number of those Bohemian matrices which are also correlation matrices. And finally, I am closing this list of results produced with the help of Maple, just giving a different interpretation of the Bohemian correlation matrices with population 0 and 1, that we have been able to provide a different proof those introduced by Robert Israel, just proving that the characteristic polynomials of these matrices, of these Bohemian and correlation matrices, encode the partition of n. That, of course, this is connected with the Bell numbers that are counting, of course, the partition of a set. Of course, we have a lot of questions to answer. I would like just to mention only 3 of them. The first of one is that we have the same table we have for the Bohemian correlation matrices for the population 0 and 1, but we don't have the lack we have with the other populations because we don't find any information, useful information in the encyclopedia. Also, it's an open question to understand inequalities, characterizing this correlation matrix by using these inequalities. In the dimension 3 is quite easy, but for a higher dimension, we are not able to give a proper interpretation for these polynomial inequalities. And also these inequalities can be very useful when dealing what is called in linear algebra, the correlation matrix complexion problem. That is no more than having a matrix with some entries unknown, and we want this matrix to be a correlation matrix, but using these inequalities provides an interesting way to solve this problem. Those interested in Bohemian matrices or in Bohemian correlation matrices, please go to the website of the Manchester Workshop or to the mini symposium at ICN last year. But even more information about the Bohemian matrices, we have the official web page for these matrices that you can visit this web page because it's full of very interesting information.
Thank you, Laureano, for that wonderful talk. I had one question that occurred to me, which is the following. So I really liked how you explained that you translate the condition of being positive semi-definite to a semi-algebraic system, so a system of inequalities, really. What I wasn't quite sure about is to understand how you count the number of solutions of that system of inequalities. Is it just plugging in sort of the Cartesian power of the population into the inequalities and counting when it is satisfied and when not? Or is there something cleverer going on?
This is exactly the point. Since the entries, ABC in this case, belong to a finite set of integers, initially 0 and 1, or -1, 0 and 1, we just run all the possibilities and take into account those satisfying these inequalities. So this is because our set of matrices is finite, and so this implies that we check if these matrices satisfy or not these polynomial inequalities. And so this is the way we count. We've been able to fill the next line here. And so, but this is exactly the same thing for other populations. The key point is that fishing dimension and fishing the population, the number of matrices to consider is finite. And so we check every matrix with maple, of course, if satisfy or not the inequalities. Any more questions? I think I have lost the connection.
Yes, Eric seems to have lost his connection. So in that case, if there are no more questions, then we can proceed with the next presenter.
Okay, thank you.
Can you hear me?
Yes, we can hear you.
Okay, perfect.
So our next presenter is Sergey Yurkevich, and the talk is titled "The Art of Educated Algorithmic Guessing."
Yes, thank you. And also let me thank you for inviting me or allowing me to speak at this great conference. So in this very short session, I will try to a bit explain my talk, my longer talk, which was recorded, and also try to promote it and yeah, explain that you should watch it. So here I start with somehow the final slide of my talk there. So this is the slide on the main takeaways and the summary. And my main takeaways were exactly three things. So that first, sequences are somehow ubiquitous, not only in mathematics, but in general in all kinds of areas of research. And yeah, so here I display just one very interesting sequence, which maybe you did not know before. So these are the Almqvist to Dillon numbers, which are related to the a priori numbers, which have very deep meaning. So my second point was that guessing, and I will a bit explain what I mean by this, allows to find structure in such, it allows to find structure very often in such sequences, and for example, prove such nice identities as this one. And the main point maybe is that GFun, which is a Maple package, makes this guessing very efficient and very easy. So this is somehow the summary. And let me now a bit explain more what I mean by those points. So first, let me start with sequences. As I mentioned, one of the takeaways is that they are ubiquitous and very important. And obviously, you would expect them to arise in enumerative combinatorics, like counting walks, or in general, any object in enumerative combinatorics. But also, they appear in many other mathematical areas, like algebraic number theory or analytic number theory. Here, I just list one particular example, which is not maybe the main interesting, but just for you to understand what I mean by these areas. But also in computer algebra, when we count or try to fast compute elements and sequences, but also in algebraic geometries, and also in other sciences, like if we interconnect in mathematics with something else, or even in biology, which I will address later, or completely other areas of research. So the main data structure we will work with are pure recursive sequences and equivalently defined functions. But let me also now mention that actually this is not the only area where the algorithms work, but only a sub area, but already a very big one. So this is a very nice class, and it is a very big one. But for example, in the talk before me, there were Bell numbers mentioned, which are not definite, but they are almost definite in the sense that, yeah, they satisfy something very similar. And there, these techniques can also be applied, for example. So, for example, a sequence, yeah, is recursive. It satisfies a linear recurrence relation with polynomial coefficients, like this one. And equivalently, the generating function will be then definite, so satisfying a linear differential equation with polynomial coefficients. So as I mentioned, these two classes are very large, and at the same time, they are very easy to handle with because they both just need finitely many data to incorporate. So you just need to save the polynomials and some initial conditions. And at the same time, there is a vast theory for both of these viewpoints in this field, and also nice effective algorithms for this class. And on the other hand, we have the guess and proof approach, which I mentioned on my first slide. So now let me try to explain a bit more what I mean by this. So it is somehow part of experimental mathematics, which was propagated already by Polya. And nowadays it became extremely fruitful because we are now able to use a computer and to somehow let the computer do the difficult or the guessing on difficult computations of this idea. So, and moreover, the two classes I just mentioned, the one class of the pure recursive sequences and definite functions, are somehow ideal data structure for the guessing. So what I mean by this, so imagine you have already a sequence and you don't know the underlying structure of it. I mean, for example, the recurrence relation. And now using these techniques, you can input the data and find the structure, but also simpler formulas. And as I mentioned, this is very efficient in practice when using Maple. In particular, when using this GFun package, which I am not an author at all. It was actually written before I was born, as you see. So I'm 25, and it was written already almost 30 years ago by Bruno Salvi and Paul Zimmermann, and it is constantly improved. And the main idea is that this package allows, at the same time, guessing a sequence. I mean, by this, as I mentioned, the recurrence relation or the differential equation from the first terms, and it does it very efficiently, and this can be used in practice often. Also, it has implemented closure properties and interplay between recursions and ordinary differential equations. So it comes actually already with Maple, so you can just run with GFun and you have all the nice functions already there. But there is a newer version which is even more efficient. So this is now the newest version, which you can download from Bruno Salvi's website. So as I mentioned, I'm not the author of it, but I was using it in the last months or years very often. And so this is already my final slide for this short presentation, but in my recorded bigger presentation, I show a Maple worksheet with some toy examples and some recent research questions, which could be answered very nicely and easily using this GFun package. And this also very nicely shows how GFun works internally. Yes, so thank you for this, for listening to this shorter presentation, and I'm open to questions now.
Wonderful, thank you very much, Sergey. I had one question. So in the longer talk, you showed that very nice torus example. So maybe this is a question that you don't have insight into, but I will just ask anyway. So you used maybe 40 or 50 terms of the sequence to get GFun to recognize the recurrence, or I guess when we should really say to guess it successfully. So, I mean, a priori, before you know anything about the recurrence, you can't really know how many terms you'll need, but is there some bound that you know afterwards? If you look at the recurrences or something, you can say, okay, you would need about this many terms for GFun to recognize it?
I absolutely understand the question. Do you see now my Maple worksheet, just for everybody to understand what we are talking about?
Yes.
So this is what you mean now. There's this list, and from this, GFun guesses this recurrence relation. And the question is why? How do we know that we should use this many terms? So the short answer is the good bound, or the what you would expect is so you take the degree of this recurrence relation, which is in this case I think 4. So we have polynomials of or degree 4 here, and the order, which is in this case 9, and the product of them plus a bit like plus 2, for example, should be the number of terms you're using, because this is how many terms here appear in the worst case. Now, the next question would be, how do you know what the degree will be if you don't know the guessing in beforehand? So you start with some few terms. In practice, it is not very difficult to compute the terms. So if you expect some recurrence relation of order 9 or of order 10, and of some degree, I don't know, 5, then you can easily compute 100 coefficients and then check. I hope this was somehow an answer to your question.
Wonderful, thank you. Yes. In the meantime, we have one more question from Rob Corrales. He asks, in your experience, do you need to tweak the default settings of various parameters of GFun to use it, or have the defaults usually been successful for you?
That's a great question. If you're using the newest version, which I said you can download from Bruno Salvi's website, then you can really use the default version, and it works perfectly. If you're not using it, I mean, if you use the pre-inbuilt version of GFun, it will automatically bound the order of the sequences you're trying to guess. I mean, I think the default is 3 or maybe 4. So in the original, I mean, the pre-built version of Maple, this would not work because then you would need to tell GFun, which you can also do, to set the maximum order, which it looks for at least 9. Yes, but in the newest version, you don't need to do this. But this is actually explained in the documentation. So there, if you now do then it tells here that the maximum degree of coefficients and the maximum order is bounded. But this is not the case anymore in the newest version. So this is why you really should use the newest version. Yeah.
Thank you very much. We have 3 minutes left for some possible other questions. So that I didn't explain this at the start, but we have a time slot of about 50 minutes. And we have 4 presentations, each of which is bounded to about 10 minutes. Initially, we have about 3 minutes left of that. And that means that we can now open the floor to further questions for our speakers. There is one that I'd like to ask of Ryan Sandford.
Hey.
So you describe this hybrid method, which is a hybrid of the 2 methods, the pre-existing one and the new one that you wrote. I wanted to ask, how is your method hybrid? Do you run both versions in parallel, or do you choose one to run first? And if you choose one to run first, then how do you make that decision?
That's a good question. So yeah, right now the hybrid is kind of very much like just one then the other. So we don't try to intermingle them or anything like that, although that could be possible in the future. And right now, the selection by default will be to run the generalization of Fulton's algorithm first, and then the tangent cone algorithm. The reason for that being is because in the preliminary benchmarking results, we were getting significant performance improvement. So usually a couple seconds faster is computing more examples, and for large systems, sometimes minutes faster. So we figured that would be the best bet to do first. And then if the user wishes, they could say, only apply the first method or only apply the second one, or try both.
Understood. Thank you very much. I have one more question. In the meantime, we get another question from Tian Chen for Sergey. Tian asks, if the sequence is neither d-finite nor p-recursive, what can we do?
So in this case, what you would, or what you could try to do is to guess some differential equation which is nonlinear. And for this, you would do Hermite-Padé approximation. So you could compute the first few terms of, for example, the square of your function and also the derivative of the square, and then try to find a linear relation between those functions. In practice, so this is not implemented in GFun as far as I know. Yes, and so therefore it will not be so efficient as if you do it in this way. Yes, but maybe I should have mentioned in practice very many sequences are p-recursive. Yes.
Okay, thank you very much. With that, I'd like to thank all 4 speakers for their wonderful talks in this session. And that concludes this session. Thank you all very much, and thank you everyone for attending. This means that the next item on the program is general networking in the lounge, and after that the program will start again tomorrow morning, or rather I say morning, but that is informed by the time zone I'm in. Tomorrow at 8 a.m. Standard Time, Eastern Standard Time. Thank you all very much, and I will be sure to talk to you later in other sessions.